main goal was to talk about polarized scattering, but since I think there was a little too much material in the lecture yesterday, I also tried to catch up with that, which means that we probably not cover all the material that I planned to, but I think that's completely fine. Can't switch the slides here. Is it plugged in here, this thing?
No.
Okay, okay, so just as a reminder, where we stopped yesterday. So yesterday we talked, obviously, what this thing is so great, you know? Did you take yesterday this picks up everything?
Yeah, it should pick up, but
okay.
Maybe it's better.
It's fine. Okay, that's better.
Yeah, it's a bit louder.
Okay. So in any case, so yesterday we discussed unpolarized PDFs, which of course, you know, it's kind of like a classical focus of structure measurements. And for example, we looked at the Hera measurements and made the case that those are, you know, very important for the PDF extraction. So in particular, getting the excipients shapes out here, valence quarks, in particular valence quarks. And we also saw that due to the nature of the extractions, in the Hera extractions, we have some access to the Gluon distributions, so in particular in the region where scale violations are large, and the sea quarks. However, the separating power is not big enough here to actually do separation of the different sea quark flavors. So this is basically the piece that I still want to address, because what we talked about the last time was the valence quark we get maybe from these charged current interactions, the gluons that we get from the PP interactions. So what is missing is in some sense looking at the sea quarks. So you could ask me why is it interesting to actually look at sea quarks? No? So because if you look at the distribution and also later on the polarized distributions, of course, you know, they're you know, you would think naively they just come from gluon splitting. No? So that's what we call the perturbative sea. So where you have the sea quarks just coming from a gluon radiation, which splits then in a Q anti-Q pair. So this is again, as often stored in this nuclear structure. So that's our first naive picture, and it's encoded in what we call here the Gottfried sum rule. That sum rule tells you if you do the F2 structure functions, you know, are the PDFs for the proton and the neutron, and you do the difference and you integrate over everything. So what you should get is due to isospin symmetry, you are expected, for example, that the U quark distribution here is the same as the neutral for the D quark. So you have an exact cancellation with the only difference that because the charges of the quarks are different, you get like a fixed you know, factor for this. So if you do this difference between the structure functions here, you integrate over all x, which you get is 1/3 from the valence quarks, and then you should get this 2/3, which is basically corresponding to the difference between the charges of the quarks, of the difference between the sea quark distributions here in the sea quark distribution in the proton and the neutron. So if you believe in the perturbative sea, that should be 0. Yeah? So because if the have an exact symmetry here, the U bar should be the same as the D bar, so it should be 0, and this sum rule should be 1/3. However, what has been measured, you see here, so this is the difference between the structure functions, F2 proton, F2 neutron, and then we have the integral, so the integral is the blue one, and the structure function is the black one, so it's the same right in front of it, it's difficult to see. You see it's not directly going to 1/3, no, so it's a little bit less. So it means you have a symmetry in the sea quarks. So I want to make sure again that so the interesting thing about this in terms of nucleon structure, the interesting is of course that this again accesses the non-perturbative structure of the proton. No? So it's something we cannot access just with perturbative physics, and it tells us about the non-perturbative structure. There's some models that I introduce later on that explains a little bit. So first, how do we access the sea quark distributions separately? So one of the most direct ways of doing this is DRELL-Yan production. So DRELL-Yan production means you have 2 protons that collide them, And then I could use leptons in the final states by annihilating a quark distribution, quark with an anti-quark here, and that produces these leptons. So that was proposed by DRELL-Yan here in 1970, observed here in this experiment. So this is like one of famous plots. So because it shows the DRELL-Yan production spectrum, and here you have this shoulder where you expect the J psi, and so at this point they didn't have enough resolution to actually see it. So they missed the the discovery of the J psi here. But this kind of just want to use this plot very quickly to illustrate some difficulties that we also later on come with the polarized DRELL-Yan if you look at DRELL-Yan measurements. So it's actually because you have these like large resonances here, you basically can only use usually so it becomes very statistically limited measurements. So if you really are only interested in the DRELL-Yan process, you can only use usually like this high mass DRELL-Yan part here, and sometimes also people are able to access this low mass thing, but they some resonances here. Okay, it was just like a side mark maybe for this moment. But in any case, so the kinematics of the DRELL-Yan process is that you measure the pair lepton pair mass in the final state. And because the mass of the electron pair is, of course, directly connected to the energy of the partons that go into the production, you get the simple relationship that the mass is equal to the center of mass energy, the partonic momentum of the target, in the case of fixed target DRELL-Yan, and partonic x of the beam. And then the other variable you have at your disposal is the so-called X Feynman, which is related to the longitudinal momentum that you measure compared to the maximum allowed. This gives you the difference between the x of the target and the x of the beam. So if you maybe do a DRELL-Yan experiment, what usually happens if you have a fixed target experiment, fixed target setup, what happens is that you probe basically a high x parton in your beam, because you measure stuff that goes very forward. So you kind of say, okay, my beam has a very high parton, has a high momentum, so it moves everything in the forward direction, which means that I hit an anti-quark in the target, which sits at low x. So your in this case, the X Feynman is more or less proportional actually to the x of the beam particle. Okay, so if you look at this at the cross section, then as I described, we basically have here this annihilation is proportional to the part distribution of anti-quark distributions in the target, and then the quark distributions in the beam, and vice versa. And as I explained basically by the kinematics, you can kind of forget about this piece, because it's very unlikely that you hit a high x beam anti-quark and a low x target quark here. So if you have a fixed target setup, what you usually measure are anti-quarks in the target and the quarks in the beam. And then in order to measure the anti-quark distribution, you basically make use of the fact that you know the quark distributions in the valence region very well, and also from that you extract the anti-quark distributions here. There are different setups. So what I here described are basically proton collision with a fixed target. So it's formulated from show you a second. But there are also setups where you have a quark anti-quark, proton anti-proton collisions. Then you reverse this here, or you have compass, especially for the polarized case. We have also meson DRELL-Yan, where you also sensitive to the target quarks, because in the meson you can have valence anti-quarks in some sense. Okay. So people have been, sorry.
Just on the slide before, could you explain why we are more likely to put anti-quark in the target than in the beam?
So, because if I build a fixed target experiment, also depending where I detect my lepton pair, also if I just require that to be very forward, so the acceptance basically selects or put this way, so if I would hit an anti-quark in the beam that carries less momentum of the beam, the X parton is at 0.001, it's like that. So that really gives my system less momentum in the forward direction, so it wouldn't go as far forward. So it's basically just this relation here from the. I mean, it's not 100%, of course, but it's overwhelmingly you can account for the other distribution, the fit. And right, so the other thing is just the shape of these distributions. So if you're sitting at high X, you're going to hit a valence quark. At low X, so you're going to hit a quark.
I'm sorry, I think I missed it. What's XT?
Oh, that's European X of the target part of the level. European X. So I have a quark in the target, a quark in the beam, and then X in one. The XT is in the target. So I'm really sitting here and coming here with my beam, and I hit it. This is kind of like a car collision. But if that car is very fast, this whole thing will go much more forward. If this car is very slow, like low X, is not going to be as much forward.
Is there a formula? Is there a formula?
So that is basically the only formula you have. So what you can measure in proton-proton collisions. In proton-proton collisions, you can't access the initial part of the kinematics. That's the main form of proton-proton collisions. You only have kind of like indirect measurements, which in the end are convolutional to all the kinematics. So what I can measure in this setup is this Feynman X. In that leading order, it gives you this relation, xt minus xb. So if I measure the longitudinal momentum of my system, that gives me directly the Feynman X. Yeah? So the fraction of the longitudinal momentum to the maximally allowed giving my beam energy. So that gives me this Feynman X, and that is the difference between the two. Yeah? So I can never access the X1 or X2 directly. I can only access the difference in proton-proton collisions. But that's the bane of proton-proton collision in general. That's why we like to do CIDIS, because CIDIS, because you have the incoming outbound lepton, you can reconstruct the maze 100%. But in proton-proton can't do this because you don't know the initial part of the kinematics of your beam, your probe. That's from. Makes sense. Yeah, so these experiments have been done for a long time. So there's one famous result from the NuSea experiment at Fermi Lab, maybe giving this result here. It's compared with kind of like predictions by PDF headers here. Yeah, so it doesn't here explicitly say, but the issue is, okay, I don't have. So the reason why you're interested in this d-bar by u-bar ratio is, as I said, you access the non-perturbative structure of the sea. And so you can ask, we have different models of the non-perturbative structure, basically, of the proton, especially when it comes to sea quarks. And so we don't know what's correct, so we want to test with that. And two popular one is called the instanton model. So you have kind of like instanton configurations in the QCD field. So if you scatter off those, you get here a helicity flip of your incoming quark, but you also produce here, for example, if you have a U quark scattering at an instanton vertex, you generate additional d bars here. So it would give you excess of d bar. So another model that you might have heard of is the pion cloud model. So the idea is that you have basically like a neutron core and then like the pions orbiting around it, accounting for the orbital momentum. So in this case, you would have U bar equals D bar. So you can test these kind of models. So there used to be this NuSea experiment, which is DRELL-Yan at Fermi Lab, which measured up to like intermediate X here. And the problem is a little bit that was consistent with both the pion cloud and this instanton vertex instanton model. And so the question was how this would develop at higher X. So in a second, hopefully we get to this today. So as you see here, so a bit the other way. So both of these here basically predict an excess of the anti-2D over the anti-2. And what you see here, the difference between this model is that the instanton vertex model also predicts how the helicity is going to be transferred from the U quarks here to the anti-quarks here. So the end we see we can differentiate between these models also by using polarized DRELL-Yan data. Okay, so to access this higher X, so there was a new experiment built, the SeaQuest experiment, and so it was basically using photons from the Fermi Lab injector, I believe, just hitting a target, which I forgot what exactly it was, but the point is that these DRELL-Yan experiments are all the same. So you hit a target, and then you have a giant absorber here to basically absorb everything else but your muon pairs that go through it, and then you have trackers to the DRELL-Yan signal. So it was highly anticipated. People thought it was an easy measurement, but it turned out not to be for various reasons that I don't have time to get into. But recently, the final results of this experiment was published, which was kind of exciting, which are these blue points here. And you see, unfortunately, that the answer is not really definitive. No? So you have various predictions here. So the naive Proton fit models, so from previous data fits from CTEC. Then you have a Pion cloud model up here. And so there are two things that happen. So the data points are kind of in between, so it doesn't help you much. And the other things is, which people cannot really explain, which is I think something experiments have to deal with, is there's like a tension between SeaQuest and NuSea. But these are experiments both done at Fermi Lab by like almost the same people. So this is kind of unclear why that happened. So it shouldn't happen. So the situation is a little bit unclear. See, NuSea goes down here and SeaQuest goes up here. Okay. Fortunately, there's another way to access the seabook distribution because DRELL-Yan, in some sense, has like a very similar process if you look at W and Z production. Because DRELL-Yan is basically proton annihilating, quark antiquark annihilating to a photon, it then creates your leptons. If you look at Z and W productions, that's basically the same thing. So you have also quark antiquarks annihilating, just you have kind of like a different flavor dependence. You can produce like a vector based, so not a photon, not like in our case at RIC, we look at W's. So right, so this was the reason to have a W program at RIC. So I think I introduced this detectors before. So we have RIC as PP collisions up to 500 GeV. The main thing that you can do polarization, which is not used for this measurement. And I guess so basically you have the same kind of measurement, just instead of D annihilating with D bar, and for if you produce a W, you have for example D U bar for W minus or for W plus, vice versa. So then by doing the ratios between the W minus and the W plus, you are sensitive also to the D bar U bar ratios from this kind of production. And so the nice thing is you can say, okay, I can also do this at LHC. In principle, it's right. LHC is of course much harder because the final state is here electron and a neutrino. So you just have to do some tricks to get the W direction or construction right. And at LHC you still at like relatively low X. But for this measurement, we are more interested in the high X because here, we like data and the models are diverging. The nice thing is for RIC, you kind of cover the same X region that we do for SeaQuest. So this measurement has been done. So okay, it's like my plots are a little bit overlapping. So the bottom line, so here, as I said, you do the ratio between the W minus and the W plus. You do it either with respect to the rapidity of the electron or the W. So one is a little more sensitive to the X and X2 as the other one. But so the rapidity dependence in effect gives you the X dependence is the same way as the XF for the DRELL-Yan production. So if you add backward rapidity, you're more sensitive to your antiquarks, and as you go forward, you're more sensitive to your valence quarks. just because you have the same situation. You have X1 of one proton, X2 of the other proton. So the resulting products will go in the direction of the quark that carries more of the momentum. So it will go from, if you hit a valence quark, it will go forward. If you hit an anti-quark, so like a C quark, it will go in the backward direction. Okay, so these are the, if you just look here at the W plus W minus here, we see that this ratio is bigger than 1 everywhere, which is basically just related to the U-quark dominance, so that's expected. So the remaining ratio between U bar and D bar is like a small correction here. So these data then have been used and fitted, so it's like a jam fit here, which is used to extract the difference between D bar and U bar. And you see that this is the extraction, and both the new star. So this is basically the fit. These are fits, basically adding more and more experimental results. So you have basically just the Silas results that I had before, which leads to giant uncertainty. And then if you add NuSea and later on star, we get this reduced uncertainty bands. And what we learn is that both NuSea and star are very, very consistent with each other, and they lead to this shape, which I would claim are not really consistent with the Pinecone model, but they don't really show the comparison. But yeah, so that is basically the extraction of the C-quark symmetry. And similarly from the NPDF here, a similar plot exists here, showing consistency between those and the reduction in the uncertainties. Okay, so at this point, there's not really, so it's of course nice to measure this asymmetry. We can't really say too much about the non-curve models at this point, but we get more information just a little bit by also looking at the polarized sea, because there we get different predictions from the different models. So as a takeaway message, you can read this at your own leisure later on, because I want to come to more kind of exciting topics, namely polarization. So most people that do nuclear physics are of course interested in some sort of polarization effects. The reason is obvious. Polarization always tells you something about the dynamics inside the system. So it's one of the best tools we have. I mean, if you ask if a cat falls on a feed, or if there's dark matter, some sort of spin effect is always at work. And of course, for nuclear physics, famously, the magnetic moment of the proton told us first that there's substructure. The other nice thing is that discovery in spin in quantum mechanics has actually nice motivational aspects, especially for people that are earlier in their career. So if Ulmec and Goldsmith first proposed this, and there's this famous quote with their advisor saying, "This is a good idea, your idea may be wrong, but since both of you are so young without any reputation, you would not lose anything making a stupid mistake." So I think that's very nice, kind of like go for it, do what you think is right. So that was the introduction of spin. So we look at the polarized structure. We already saw yesterday that if you go to a collinear leading twist picture, that structure is described by 3 Proton distribution functions. Okay, so we have the unpolarized one, and the helicity one, and the transversity one. So first, we concentrate here on this helicity distribution, which is probably more well known and has been measured for a longer period of time. So as we saw yesterday, the helicity distribution, of course, gives you the probability that you have a longitudinal polarized photon, and you're asking, okay, what's the probability that a quark carries the same polarization, so that quark basically contributes to the polarization of the photon. This picture kind of shows you already a naive way of to measure it. So what you do is you polarize your beam. That means that the photon exchange is polarized. And because the photon has spin 1, it can only couple to quarks which have the opposite polarization. Because a quark has spin 1, spin 1/2. So in order to absorb the spin 1 of the photon, it has to flip around. So you can only do it with quarks that have the opposite polarization of the photon. So what you can do then, you can measure with two different beam polarizations, so maybe beam parallel and parallel to the target. And if you look at these cross sections, the difference between the cross sections and the difference between the quarks that are polarized along the proton direction is the other way around. So that gives you this probability that the quark has the same polarization as the proton. Then, as we also saw, you can do it in a semi-inclusive process, so you can measure the hadron and you knock out. For example, if you want to know if you're more likely to hit a U quark, you have a pion production, or if you have a if you have a kaon, then maybe you're more likely to have a strange quark. So similar to the unpolarized structure, now this cross-section difference is related to structural functions, so which you're also familiar with. So you do the difference, which we always call in experimental physics, you measure a symmetry here. In this case, a double spinor symmetry because we polarize beam and target. So the nice thing with this is that you cancel out the whole unpolarized structure, and you're left with a polarized one. So similar to the unpolarized one, you again can parameterize it with two structure functions, but it's different from the unpolarized case because now the relation between the structure functions are different. So first of all, the nomenclature is more inconvenient because we have this lowercase g, which is the same as for the PDF. And then we have this G2. And you see you have two terms. No? So we have the leading one that goes with G1 that you're probably familiar with. And then we have a subleading one that's suppressed by 1 over Q, so that means it's higher twist, which has this combination G1 plus G2, which we call T. So it's a twist-free function, so they're not, so in the unpolarized case, they're kind of on the same footing. Here, they are not on the same footing anymore. There's a different term here, and so this term here, which goes like cosine theta, that theta tells you the angle between the photon direction and the polarization direction. Because this argument that I gave before is of course only true if they're actually, head-on. So if the photon is not head-on, you have like a transverse component, so you have to account for that. So if you have the photon momentum is parallel to the nuclear polarization, you only have this leading term G1, and then the other one is suppressed. So I also introduced the last time the hadronic tensor, and we saw that the symmetric part of the hadronic tensor, which is you measure when you average over the nucleon spin, can be parameterized by the unpolarized structure function. Similarly, now if you use the antisymmetric part, that can be parameterized by these structure function, in particular if you add leading twists, so you only have this the G1 here then. And if we compare to our quark correlation matrix and we expand it in terms of observables, we see that this is then directly proportional to the PDF G1. So the G1 structure function is similarly as F2 is related to little f PDFs. The G1 structure function is just the sum of the quark flavors of the helicity distribution functions times this coupling here of the quark charge squared. Okay. So there's a small side remark. So I have two slides in the end for this. So this whole discussion is of course only true for spin 1/2 targets. So as our proton is that we are in principle interested in. If you go to spin 1 targets like deuterium, you get an additional structure function because you have an additional polarization state in the tensor polarization. So you get an additional structure function which parameterizes that. Okay, so I think one of the most famous plots relating to G1 is related here to the so-called spin crisis or the spin puzzle. So it's also an interesting kind of story because if you look up, people first are interested in the nuclear spin structure. The quark model was so fully, in kind of the naive quark model of the proton was so fully established that people thought, okay, you don't really have to measure this because we know it's going to add up to the spin of the proton. So lo and behold, it was measured. So this is like the G1 structure function. This is the integral. And you see it's not adding up to a half spin here. And so this is, that was measured by the EMC experiment, and that led to the spin crisis. And it's kind of like an example how, spin is like a really, really strong test for our, understanding of the proton. So if you really want to understand something, you basically have to add spin. That's a famous saying. Or there's another famous saying that says like spin kills more theories than any other observer. Okay, so The good thing for us was that this kind of discrepancy that the quark spin doesn't explain the nucleon spin led, of course, to a lot of interest in our field and a lot of activity. So why a lot of activity? So it directly tells you there has to be more going on in dynamics. No? So we started with this naive quark. People started with a naive quark model. So this was basically thrown out by this measurement. So then the question is, where does the additional spin come from? So the obvious part is QCD corrections. So gluons can carry spin, and we're going to talk about this. It's going to turn out that that's not enough. And then finally, of course, the holy grail is orbital angular momentum. So if you have to measure the actual orbital momentum in the quarks, in the gluon, then the proton, they can also contribute to the spin of the proton. So as I said, this spin crisis led to a lot of activity in the field. So this is kind of like I think a little bit outdated slide of what kind of the history. So of course, that it's a pioneering experiment at SLAG in the 70s and 80s. Then at CERN, I think NMC is missing here, and you had like EMC, SMC, and COMPAS. So all using the muon beam. It shows they're actually still taking data. Then we had Hermes pioneering a lot of measurements here, and then of course at JLab 12, we have class and about 8 spin experiments. And here in this community, often it's forgotten. Of course, at RIG, we have a very rich program in polarized PP, also Transversity that also we'll talk about. So just a very quick look at the experiments. I think this is probably familiar to many of you. So a lot of pioneering measurements, especially for the transverse spin, were done by Hermes. So Hermes was using the Hera electron beam, so 27.5 GeV. So it used an internal target to this to the Hera beam. So you basically you're still running Hera, no? So Hermes was kind of like parasitically using the electron beam, which means that they couldn't really disturb it, to use in the collider. So I think for me the most distinguishing part of the Hermes experiment, they have this like septum plate here to basically isolate the beam pipe from the magnet. So every time you see a Hermes talk, they always put a lot of emphasis on how they do acceptance corrections and so on. But I think the main reason for that is that Hermes has like the worst acceptance of any experiment that the world has like a very good acceptance because they don't have this magnetic field in the middle. In any case, but the advantage is because they use this internal gas target, they have like a very clean, without nuclear effect target, because they basically the blow gas inside the beam of polarized hydrogen and other things. Then you have COMPAS. It's a more traditional fixed target experiment. So it's basically the same setup as NMC, EMC, and SMC beforehand. So it uses a beam from the SPS. So the protons hitting production target and the muons from this. The advantage is you have a very high energetic muon beam, 160 GeV usually, so you reach lower X. It has more statistics than Hermes because the disadvantage of the gas target, of course, that you don't get that much statistics. It's like a solid target. But since you have a secondary beam, you can't really go much higher. The nice thing with the muon beam principle is also to have less radiative corrections. And then the spectrometer is more classical. There's 2 stages. Good acceptance, good coverage, very uniform. They have 2 actually spectrometer magnets to cover small and large areas. So it's a very nice setup. So as I said, COMPAS runs a more traditional target. So we have deuterium and proton. So comparing the 2, of course, allows you to do some flavor extraction. The disadvantage with these solid targets is that you don't have pure proton, pure deuterium, of course. You have here lithium deuterate, and here you have ammonia essentially, which basically, especially for the deuterium target, leads to less polarization, and you have some dilution, and you have some nuclear factors that you have to account for the cross sections. But I think most nowadays people, they don't have a big problem with that because the deuteriums very actually loosely bound. And finally, I think another experiment, of course, it has to be mentioned here is class. So here the defining character is, I think, which is kind of unusual, is this toroidal magnet for the small angle scattering, and has an additional magnet here for smaller angle, the solenoid. But as all the others they have all labeled PID with bridge detectors, so Hermes, COMPAS, and also class on the bridge detectors for PID, very good tracking. So on. Okay, so these are the players. So look at the world data. So this is already a little older slides, but the main reason I want to illustrate here is that if you look at the world data, proton and deuterium, so you can't really see it. So red is compass. Then you have also Hermes and these like weird crosses and then all experiments. So the main point is because you only look at fixed target experiments so far, you only cover this area here. So, which means that you can't make use of scaling violations to extract the Gluon polarization. You can just measure in the scaling regime, so you can just measure the maybe the sum of the quarks here. But you have like a fair number of data both for proton and deuterium. So if you look at extractions, mainly before you had the majority of the RIG data in there. This is kind of what comes out. So it's like one of the classic fits from the DSSV group doing the polarized one. So there's other polarized fits that exist also from the German group now and from NPDF. But DSSV is kind of like the classic fit that uses a parameterized approach. So these are the data points that go in there. So you have the DIS data, you have CITES data, to get some flavor separation for both pions and protons, and you have the deuterium target and you have proton target here. And you also have the first PP data here by zero production, blend production from Phoenix and Star. But at this point, it's the first data is little statistics, so you don't really get the delta G very nicely out yet, but it will change. But in any case, so what I just want to point out here is that you don't really have a flavor separation here, so you have U bar and T bar here, but you get from this some very precise results. For the U bar and D bar quark polarizations, the uncertainties are relatively large. Not quite consistent with zero, but still quite large. And then strange quarks also more or less consistent with zero. Same with the gluon, with the exception of the high X region. Okay, so that's the status for like the main part of the RIG program on the gluon polarization of the quark distribution. So before I come to the gluons, I just want to give you this promised kind of small excursus on this tensor polarization, which is also not really the focus of me, so I can only tell you what I write more or less. So the idea is that you have a spin 1/2 target, and also you can polarize in these two states, -1/2 and +1/2. So the spin kind of goes, because you only fix the longitudinal direction, you can kind of imagine it goes kind of like in the circle here or the circle here. So people say, okay, that looks like a peanut, or has this kind of shape. So if you have a tensor polarization, you have a third polarization state where the projection is 0. So you kind of have this middle blob here where the spin can be. So people compare that to the donut. So now you can have 3 instead of 2. You can have 3 structure function at leading twists. So you have F1, G1, the same as we had before. So unpolarized, the difference between the M ±1/2 states. But now you also have this B1, which is the difference between this donut shape and kind of the average of these peanut shapes. So you have so that because there's leading twist, that's a Platonic interpretation. So the Platonic interpretation is exactly as I said. It's the difference between having a parton in this spin state or this spin state. So the interesting thing about measuring this tensor polarization effect is that they are very closely related to nuclear effect. Because you have a deuterium target, if you adjust the proton, you don't have tensor polarization. So you have to go to the deuterium. And so only if you have nuclear effects, you actually, you can get so only if there are nuclear effects, you can imagine that there was an effect on the spin set of your parton. If you don't have nuclear effects, you just have a proton sitting here and neutron sitting here. So if you scatter on it, so you won't have this, this tensor polarization effect. So that's kind of like the interesting thing here. So there was a measurement by Hermes. They in fact saw a non-vanishing value for this tensor polarizing structure function that rises at very low x, and so it's supposedly interesting because that rise is in shape similar to the rise of nuclear shadowing in that respect. So that you kind of have this connection again between nuclear effects that are important for this tensor polarization and this nuclear sharing effect. Okay, so these are the quarks that come to the Gluon polarization. So as I anticipated already, here really the game changers are is RIC, no, not LHC. I think it's just a carryover from the unpolarized case, but really RIC because you have polarized protons colliding. So if you have a polarized proton, the advantage is now that you have the scattering is dominated by these kind of processes. So you have either blue quark or quark. No? And it's similar as a question, which was very relevant, of course, in with the DRELL-Yan. So how do I differentiate between the two and so on? The answer is I cannot. No? I can only say, okay, if I, for example, observe a jet with a certain PT, then I can only say, okay, the probability that I have this process or that process is that much. I just calculate the convolution over the PDFs accordingly. And then I do a global fit, and I hope that this global fit, if I put in enough data, I just converge to a minimum, which gives me some sensitivity to the different distribution functions. Okay, so I put in, if I do these double spin symmetries in PP, so this is kind of what I get. I get the convolution between the PDF of the first proton, the PDF of the polarized PDF of the first proton, the polarized PDF of the second proton. Then the elementary scattering cross-section here between the partons involved. This is a platonic ALL that goes in here, and then depending on what I measure, I have a fragmentation function here or not if I have a jet. So this is kind of normally how the process served here. In this case, a quark and a gluon scattering of each other, and then either have like jet measure or hadron. So this has been measured, and one of the first high precision measurements were 2009, the star jet data. So you see here, this is plotted with this jet PT. You see this data is rising, so it doesn't not necessarily mean that there's a gluon polarization, because as I explained, if you go to high PT, at some point in time you have quark gluon dominating, and since you know that the quark distributions are polarized, naturally your data points will show significant symmetry. What is important here, if you look at the prediction at this point of DSSV, which has like a very small gluon polarization, these are significantly below the data points. So this data points vaguely hinted at the first significant gluon polarization. And that led, I'm not sure if you're probably too young for that, but at the time, I don't know, it's probably like 10 years ago or so, a lot of press interest. So like there was like, that was covered quite a bit because it was the first indication that was actually a non-zero gluon spin contribution. The caveat is, and it's one of the reasons why we need the EIC, you see this plot. So this plot shows you the most likely value and the 90% confidence region for different integration limits. So this one is x of 0.05 to 1. And that is chosen because that is the region that RIC covers. Yeah? So here you see you are significantly away from 0. So you can claim that where you measured, you actually found a non-zero gluon polarization. That's not true for the whole integral. So if you start from 0 and go to 1, that's not true. So basically, you don't know what happens if you measure down to 0. And that's of course one of the domains of the Cs. So experimentally, we got delta G of 0.2 with large uncertainty, which is still quite not enough to make up all the proton spins. So the remaining wisdom is that the remaining part is that all angular momentum. This is also consistent with lattice results. So if you calculate on the lattice, so it's like here from Phi Lu, they did a lot of work on this. They get something like this that quarks carry like 40%, gluon like also roughly 40%, the rest of the quark angular momentum, orbital angular momentum, which is consistent with the measurements so far. Okay, what about the C? So the we saw that we have this asymmetry in the unpolarized C. So the natural question is, okay, what about the polarized C? So here, introducing polarization, as in many other situations, has quite an advantage, because now these different models, so some of the most popular models, Instaton and Pinecroft model, actually give you different predictions. And the reason is if you look at the pion cloud model, you have pions that kind of orbit around. So the pion here has been 0. You know? So maybe it means that you don't expect the antiquarks that are sitting in the pion to contribute to the sea quark helicity. Whereas in the internal model, that's not the case, because you have this kind of more intricate kind of like spin transfer from valence quarks to sea quarks, which also flip the helicity when you go here, for example, from the right-handed U quark, you produce here these antiquarks. So that basically leads to the prediction that you get more polarized U quarks than polarized D quarks, because part of the U quarks basically reduce the polarization of the D quarks. So there's quite a bit of motivation, even though obviously the C quark polarization is so small that it will not contribute to your spin puzzle overall, but it tells you a lot about the non-material structure of the proton. So how do we measure this? So again, you can measure this at the W production, and this time you look at single spin symmetries. And so the idea is that because the W has this maximum parity violating coupling, it only couples to one of the spin states. So if you have a polarized beam, and then you couple to the W, you basically just select one of the spin states. And as before, the angle that you look at, so if you look, say, at your polarized, actually here, indicate, so if your polarized proton comes from that side, so we have the same thing as we explained previously. You know, so if you hit an antiquark, so the situation where you have a U bar coupling in your polarized quark coupling to the D quark in your unpolarized, then the remaining product will go to the back, you know, because the D quark here of your second proton will have so much more energy. So if it's the other way around, so if you couple here the D quark distribution, in this case here, to the anti-U of the other one, so then you will go forward. So it's kind of what you see here. So this is with respect to the pseudo-rapidity of the W. So pseudo-rapidity is 0 is in the middle, and then -2 is backwards and 2 is forward. You see the predicted asymmetries of the different fitting groups. And you see, what you see is that if you go in the forward direction, they all converge. You know? And then the reason is because this is sensitive to this valence quark polarizations, which are very well known. So all the groups have the same predictions. If you go to the backward directions, they're diverging, because here you become sensitive to the anti-quark helicities, and so they're less well known, and so all these predictions kind of diverge. So this is a measurement. I didn't put the reference here, but it's a PRL that has most of the star data. These uncertainties here don't come out. But the point, it was measured with relatively high precision. They don't know for measurements as well. So you see kind of here with respect to the lepton pseudo-rapidity, which is correlated to the pseudo-rapidity of the W boson. So you get these large asymmetries in the forward regions, because that's where you have this valence quark. And the valence quark helicity coming in, and you see that the theoretical uncertainties are also not very large, but in the backward region where you are sensitive to the anti-quark, the uncertainties kind of blow up. So you can put this in the fits. Unfortunately, this was, I'm sure there's an update by now. It's from 2014, the NPF fits, and you see that the star data significantly reduces the uncertainty, so go away from the green to the red on both sides. However, they're still quite large. So I don't think it's like a very definitive statement can be made from that at all. But I have to say, I haven't really paid attention in the last couple of years. I think the data has been updated, and probably the update fits I'm not quite aware of. Okay, so the last thing I want to mention in terms of it's already the hours over. See, okay, it's exactly right for the break. To finish the helicity part, so we saw if you go to low X, you can learn an interesting thing about the non-material structure because you access the non-material C. You can also go to high X, so which maybe has a little bit less attention. So the interesting thing about high X, you think, okay, it's like, well, it's quark, I don't really care about this. But if you go to very, very high X, where the parton is basically carrying all of your photon momentum, you're in a situation where you can make a lot of perturbative algorithms anymore, because your partons basically have so much. So it's basically like, you know, one parton carries like all the energy, and the rest is kind of like corrections. So you can make a lot of perturbative calculation that, and you can make some perturbative predictions how the parton distribution functions should behave. So there's this older paper here by Brodsky, which comes up in its counting rules. So you expect, depending on the polarization state of the quark, that you have either this 1 minus x power 3 or the negative 1 to the power 5. So it's again, I believe, has to do with this like spin flip that you do if you have the other helicity, but I'm not entirely sure, to be honest. But okay, so this is basically the expectation you get from perturbative calculations in power counting if you have an orbital angular momentum. And then you see this kind of predictions here, and then so they can predict that you go for this ratio then of the polarized or the unpolarized distribution functions. You should go to 1, but the data points, if you look at this for the D quark, did not confirm with that prediction. So the question was why? And then one explanation is if you introduce orbital angular momentum in your wave function, you get here an additional factor introduced, which helps you pushing this curve lower down and agree with these data points. So it's kind of like a motivation to extend these measurements to higher X to prove this more. Okay. Yeah, so the effect of the orbital motion on the X might maybe significant. So maybe it's a good time to stop before we go to the transverse structure.
So we finish 1 hour. So other question? The room here. Yeah. From the top. Sorry.
How do you measure the angular momentum of the speed?
The orbital angular momentum, yeah.
How do you measure the percentage in the total speed?
Say again,
how do you measure the part of the angular momentum in the speed total?
Oh, the total. Yeah, so different. So the answer is difficult. The most direct way is so if you want to access the orbital angular momentum part, as we show later on, so this is something you can access principally generalized part distribution functions, GPDs. There is, if you measure TMDs in come to where you transverse momentum dependent ones, distribution functions, there are a lot of model dependent connections between orbital angular momentum and this distribution function, but nothing really, directly. So I think the kind of like so when people do, so either they go say, okay, we measure the Gluon polarization and the quark distribution, and then we subtract that from the total spin and gives you my orbital angular momentum, or I go with the GPD. There's a sum rule that allows me to access the orbital angular momentum and I measure it that way. There's some discussion how far this quantity is actually comparable, so there's like some technical details, but that's like roughly like the idea behind it. But I think it's a little bit of a red herring if people talk about orbital angular momentum. Of course, like a very interesting question, but for that you really have to kind of map out like the full dynamics. So you have to measure. People say you have to measure DPDs, but at this point, the data we have only allows us a very model dependent. So I show later on some first extraction of that from DPD measurements, like in the end, but they're still highly model dependent. I think the point I want to make is like even if you don't have this, so the spin part in that sense is like like a nice motivation, so you don't understand it. But on the way to that, all the other measurements already tell us a lot of things about other non-perturbative features in Proton.
We have other questions here. I don't see anybody from the chat. So okay. Okay. Thank you, Anselm, for the lecture.